Hello, my name is Shushu Shi, and I am a master's student from the University of Ottawa. I'm here to present my poster, Computational Optimization of Differential Mobility Spectrometry Parameters in Lipidomic Analysis. Glycosylsphingolipids such as alpha and beta glucosoceramides and alpha and beta galactosoceramides are stereoisomers differentially synthesized by gut bacteria and their mammalian hosts in response to environmental insult. Thus, lipidomic assessments of alpha and beta glucosoceramide and alpha and beta galactosoceramide is crucial for biomarker discovery and pathomechanistic studies. However, simultaneous quantification of these stereoisomeric lipids is difficult due to their virtually identical structure, as the only structural difference between glucosoceramide and galactosoceramide is the axial versus equatorial position of the 4' hydroxyl group of the sugar hat group. Differential mobility spectrometry as an orthogonal separation of liquid chromatography electrospray ionization tandem mass spectrometry can discriminate stereoisomeric lipids with different functions. Currently, the development of an LC-ESI-MS method for lipidomic analysis demands intensive manual optimization and relies exclusively on the availability of synthetic lipid standards. Where synthetic standards do not exist, method development is not possible. There are 6 different DMS parameters that contribute to the eye intensity detected following LC-ESI-MS.
The parameters are separation voltage SV, composition voltage COV, modifier gas concentration and flow, DMS offset, and temperature. These parameters can be optimized to ensure the maximal separation and resolution for glucoceramide and galactosoceramide. For example, optimal combination of SV and COV is sufficient to separate glucosoceramide from galactosoceramides. To determine this SV-COV combination, a labor-intensive set of experiments must be performed wherein COV is rammed at each target SV to empirically determine which combination separates glucosoceramides from galactosoceramides. Note these values are specific to each pair of stereoisomers and thus must be determined empirically for each molecular species a user chooses to analyze. This requires the user to have access to all necessary standards. Ion intensities are then plotted for the different COV values at each SV in the form of an ionogram. In this example, at lower SV, separation of the pair of stereoisomers is not achieved. At higher SVs, we see 2 peaks, representing the 2 optimal COV values for selecting this particular glucosoceramide and galactosoceramide. When SV is changed to alter the differential mobility of the ion, for instance, to optimize separation of a particular pair of glycolipids, a new COV will be required to correct its trajectory. Optimization of both settings enables separation of stereoisomers. In addition, we can improve separation by optimizing all 6 DMS parameters, but optimal separation may come at the expense of intensity. DMS parameters are empirically optimized sequentially, as demonstrated by the heat map of intensity values plotted for different SV and COV values. To investigate other parameter values, this experiment must be repeated for all possible combinations of DMS parameters. However, an in silico approach enables simultaneous optimization with fewer empirical assessments. We show here that a supervised machine learning approach can predict lipid intensities for all 17 beta-glucosoceramides and beta-galactosoceramide stereoisomers as a function of the DMS parameters, SV, COV, and modifier gas concentration. We can use the predicted intensity to further optimize DMS machine parameter values to achieve maximal lipid separation. To achieve this, we implemented a 5x10 layer neural network to predict the effects of SV modifier gas concentration on ion intensities at different COVs. We use the ATOM solver with weights initialized by Glor uniform. To optimize our network, we determined the combinations of hyperparameters, including the choice of a loss function and the activation function of the inner and outer layers that would yield the best prediction outputs. All findings were subjected in a 5-fold cross-validation for each of the 17 stereoisomers.
Peak detection algorithm reconstructs the ionogram based on the predicted intensity and assesses when separation occurs at a specific SV and a COV for a given glucoceramide and galactosoceramide pair based on the ionogram's shape. A confusion matrix was established to assess the sensitivity, specificity, and accuracy, where a true positive is a correct prediction of separation, defined by the detection of two peaks at a given SV across different COVs, and a true negative is a correct prediction of the lack of separation, as indicated by one peak at a given SV across COVs. We found that our highest scoring hyperparameter combination consisted of soft plus as both the inner and outer activation function, and mean squared loss error as a loss function. These combinations were able to yield a sensitivity of 54%, a selectivity of 99.7%, and an accuracy of 99.6% for all pairs of glucoceramide and galactosoceramide stereoisomers tested. Predicted COV for both the apex and valley of the glycolipid stereoisomers were highly correlated with the empirical results following linear regression analysis of R-squared values of 0.93, 0.89, 0.94 respectively. Intensities of the apex were also significantly correlated with R-squared values of 0.89 and 0.85. Predicted valley height indicative of the extent of separation was somewhat less well correlated with the R-squared value 0.68. Taken together, these data provides proof of concept that a supervised machine learning approach can be used to predict the intensity of data obtained across different SVs and COVs, and thereby establish at least 3 of the DMS parameters necessary to separate glucosoceramide and galactosoceramide stereoisomers. We are extending this model to predict the impact of the 6 parameters simultaneously. This approach will enable DMS methods to be developed faster and more efficiently, even in the absence of a complete repertoire of synthetic standards. Thank you very much.